So today's topic is a mainstay of mid-level algebra, and it's called solving systems of equations in two variables. The topic's been a particular challenge for math teachers for ever. It is a beautifully pure algebra concept and a magnificent example of applying simple mathematical structures to an easily envisioned but still relatively complex concept. That's all well and good, but the drawback is that it has no discernible application to what we call the real world, or at least what decent people like to call the real world. In this sense, it has the same drawback as about 80% of the rest of the stuff that you'll find in the Algebra 2 curriculum. To be sure, math teachers have tried valiantly for years to shoehorn real-world situations into this concept. If 2 shirts and a sweater cost $60 and a shirt and 2 sweaters cost $75, how much does each cost? But the truth is, pairs of linear models which intersect in a single point is certainly an interesting concept in mathematics. And it does tend to occur frequently in nature. The average butcher, baker, or candlestick maker is not likely to encounter an opportunity to use this particular piece of math and discover that intersecting point. All this, however, does not make the concept any less interesting or the process any less elegant. Neither does this fact put the subject in any peril of being removed from the standard Algebra 2 curriculum. So your school teacher, by way of your local school board, is requiring you to learn how to solve a system of equations. Let's talk about what that means, and then we'll describe the 3 generally accepted methods of making that happen. I am not going to demonstrate the process for any of them right now, though, because I'm not here to get you to understand how to do them. I have later videos that will do that. Right now, I just want to make you understand what we mean. The first method, perhaps the simplest and definitely the most intuitive, is called graphing. Now, you're being given equations in 2 variables which are mathematically interesting because they visually demonstrate how one variable relates to another. In the examples we'll use here, those equations are linear, and therefore it's not a big deal for us to represent those equations on a graph in the same frame of reference at the same time. Each line then represents the infinite set of points x, y that satisfies the original equation that created that line. Now, you can graph these either by hand or by using technology. And the goal is to use your eyeballs to see exactly where the 2 lines cross over each other on the graph. That magical point is the x and y value that satisfies both equations at the same time and is therefore the solution to both equations. Assuming that your lines actually cross each other and aren't actually parallel, which would indicate that there's no common solution to the 2 equations, and aren't concurrent, which would mean that every point on both lines is simultaneously a solution to both. The benefit to using the graphing method is that the process is intuitive and finding the solution is easy. You look for it, there it is. The potential drawbacks are the possibility that you might make a mistake with your graph, and that you can only find a perfectly accurate solution if your 2 graphs just happen to fall right on an integer intersection on your graph, which happens almost every time a teacher gives you an exercise to do, but which happens virtually never in the messy and inconvenient real world of modeling. The second method is called substitution, and it's kind of a neat little deal. To understand what's happening here, you first got to get that each of these 2 equations are 2 completely different pieces of information, each with their own set of solutions. But if I were able to take one equation and sort of smash it inside the other, then the infinite solutions along the one line would get narrowed down to just the one solution that's also shared by the other. So to do substitution, what you do is fix and rearrange one of the equations. So instead of saying, here's how the 2 variables interact with each other, it says, here's one variable as defined by the other. Put another way, x is y, only changed by these other numbers. Well, now that I know what x is, I can take that one piece of information, one line, and put it into the other piece of information, the other line. That's a nifty bit of sleight of hand. By taking one equation and putting it inside the other, what I can do is I can make it so one of the variables just doesn't exist anymore. Now it's an equation in only one variable. Solve that, and you have half your answer. Once you have half the solution, either of your original equations will be happy to reveal to you the other half of the solution. The big drawback to the substitution method is that it's not particularly intuitive, and for a lot of people it feels kind of clunky. It's certainly not anything that normal people can just do in their heads. The benefit, though, is that it always works, and if there is a common solution to the 2 equations, substitution will find it, precisely. The third method is called elimination. And what it does is takes the two equations and massages one or the other or both of them so that they go together. And when they go together by a particular mathematical definition, you can smash the two equations together in such a way, you can add them basically, to get rid of one of the variables. Just like we did earlier with substitution, only this time we're doing it in a much more elegant fashion. Bet you didn't know you could add equations together, did you? And that new third equation that results from smashing those two together only has one variable in it, and so that reveals to you half of your solution. Once again, when you have half your solution, either of the original equations will be more than happy to reveal the other half of the solution. A lot of people prefer the elimination method because it just naturally tends to keep things neat and tidy. But it only works better when the original equations were neat and tidy to begin with, like with whole number coefficients and already arranged in the right fashion. So there's 3 ways to find the common solution to 2 equations in 2 variables. Now, I've had to do this a bunch of times in my life, but I'm a math teacher. I've never used it to maximize my garden's yield, or to buy an optimum number of movie tickets, or to make sure my concession stand is making maximum profit, or even to figure out how many shirts and sweaters I can buy. It's just not that common in what folks like to call the real world. But it is really a neat thing you can do with math. And math is full of really neat things. And if you look at it the right way, and if you get kind of good at it, and if you can keep from getting a teacher who beats all the fun out of it, math is a little like art, only with numbers and relationships. And I may not be a very good artist, but I like to splash the paint around every now and then. So, to sum up, an equation in 2 variables draws a line of solutions. Linear equations draw straight lines. Another equation draws a second line. You can figure out where the 2 lines cross each other by graphing them on a piece of paper, by substituting one equation inside the other, or by massaging the 2 equations so that adding them together eliminates one of the variables. Hey, me! Which of these methods should I use? Well, other me, that depends on an awful lot of things. If you have graph paper handy and you're good with using it, and you don't mind getting potentially an imperfect answer, then graphing may be the solution for you. If one of the equations is already solved for a single variable, then maybe substitution will work quickest for you. And if your 2 equations already look the same and already are sort of arranged in similar formats, then maybe elimination works fastest. The only right way to answer that question is to practice each of them for a while and then pick the one that your brain thinks is best.